All right, now we're going to look at number 10. So let's unpack everything in here. Again, we talked about one of the biggest problems you guys had on your first exam, and I think with some of these problems, we're getting overwhelmed because we're not really reading the full question. So a subject, 75 kilograms, so we have his body weight, has a functional capacity of 9 METs. Calculate a workload in watts on the Monarch cycle ergometer that would equal 70% of this subject's functional capacity. Okay, first of all, if we know that we're talking about a cycle ergometer, we know we're going to be using the leg cycling equation. And if we're talking about functional capacity, that can be reported, that intensity level can be reported in multiple ways. We could be looking at METs, we could be looking at heart rate, we could be looking at VO2 or oxygen consumption. All right, so we have 9 METs here. That is essentially the maximal level of intensity this person can hang with. So in order to convert that to a VO2, we would simply take those 9 METs and using that number 7, we're going to multiply that by 3.5. And that's going to give us a relative VO2 in milliliters per kg per minute. All right, so let's see, 9 times 3.5 is 31.5. All right, so now go back to your question. So we want to calculate a workload in watts on the Monarch cycle ergometer that would equal 70% of this subject's functional capacity. So our VO2 for this equation is not going to be 31.5, it's going to be 70% of 31.5. So 31.5 milliliters of oxygen per kg per minute times 0.7, because we want 70% of that intensity level, which is going to give us 22.05 milliliters per kg per minute. All right, so we've got now our cycling equation where we have our VO2 reported, and we can actually start to work from that angle now. 22.05 milliliters per kg minute. And I don't know if you remember, in that equation, we had our resting and our horizontal component. Those are both 3.5, so we're going to go ahead and sum those as 7 plus 1.8 times our work rate divided by body mass, which if you remember, we're on number 10 here, which was 75 kilograms. Okay, so let's take a look at what we know about workload here. Okay, we need watts. Workload typically comes in kilogram meters per minute, and all we would need to do is divide that number by 6 to convert to watts. So again, we have some extraneous information. The Monarch cycle here, we would only really need to account for that as far as the distance of the flywheel traveling. So each revolution of that wheel would translate into 6 meters of distance. We don't really need that information. We're going to be calculating workload as a kilogram meter per minute situation there that we can just convert straight over to watts. So let's just start plugging and chugging. We need to get rid of our 7 here, get rid of our 7 here, which is 15.05 equals 1.8 times our work rate divided by 75 kgs. So we need to multiply by 75 kgs, multiply by 75 kg, get rid of that over here. So let's see what that is. That gives us 1,128.75 equals 1.8 times the work rate. So we're going to divide by 1.8, divide by 1.8. Which gives us 627.1 kg meters per minute. And again, I told you 627.1 kg meters per minute. Use your stoichiometry tree. Remember, 1 watt, it would help if you could see what I'm writing, equals 6 kg meters per minute. So we're going to divide 627.1 by 6. And now my rounding is going to be a little off because I did not retype that into my calculator. That's going to give us between 104 and 105 watts. So if I was prescribing, I would just say stay above 100 watts, if that makes sense. Right above or right sitting at 100 watts. Okay, so that is our answer. Now, you see, I kept everything in lines where you can follow what I'm doing. That's another way that I can give you partial credit. Make sure that you're very methodically writing all of this out.